Salam, peace be upon you. My name is Mohammed Layiq Sediqi, the father of Holophase. Remember the language we are learning. There is one field, phi, the holophase. One continuous cyclic movement from which all of reality unfolds. When phi begins to change, its first derivatives appear, and with them, the three dimensions show themselves at once. Time as omega, space as k, and motion as v, built from both. Every higher derivative is a finer question about how phi changes, and each one casts three shadows together: a time shadow, a space shadow, and a motion shadow. These echoes mix and weave into one another, forming the patterns we call fields, particles, bodies, thoughts, and worlds. In this picture, everything that exists is a living tapestry of phi, endlessly echoing through its derivatives and their dimensional shadows. Today, we focus on one essential component of the epistemic firewall. In this part 26, we confront the most common and dangerous inferential error. We define the firewall mechanism, causal versus correlational constraints. This is the process that rigorously distinguishes between a mere statistical co-occurrence and a genuine, intervention-robust causal relationship. The core revelation is operational. Correlation is co-occurrence. Causality is intervention robustness. A causal constraint survives controlled changes while preserving lawful omega k v relationships. The skill you will gain is that of an intervention designer. You will learn to test any claimed if-then rule not by observing more data, but by actively poking the system and seeing if the rule predicts the poke's consequences. Our core question is precise. How do we know if a relationship between two patterns in phi is causal or merely correlational? This question targets the leap from description to action. We observe the tapestry of phi. We see that when one thread, which we can call A, has a certain pattern, another thread, B, reliably has a corresponding pattern. They are correlated. We are tempted to infer a rule G, A causes B. This is the most powerful and dangerous inference in science. It is powerful because if true, it gives us control. Change A, and you can predictably change B. It is dangerous because if false, our attempts at control will fail, or worse, cause harm. The firewall's causal check exists to block this leap until it is validated by a specific rigorous test, the intervention test. Why is this check necessary? The failure mode it prevents is the illusion of control. We mistake a side effect for a lever. We waste resources, design faulty policies, and build broken technologies based on correlations that have no causal power. In medicine, we give useless treatments. In economics, we implement destructive policies. In physics, we attribute effects to the wrong force. The causal check replaces hope with a mechanical test. Let us build this from first principles in holophase terms. We have two derived patterns from phi. Let us denote them as functions of phi and its derivatives, A of phi and B of phi. We observe through many windows that A and B are correlated. Their values move together in a statistically significant way across many phi sentences. We can write a correlational constraint seq-intronize. The statistical association between A and B is non-zero, as measured by a specific metric, for example, correlation coefficient R, within a defined scope S. This is a legitimate rule. It is a descriptive rule. It says, when you see this, you also tend to see that. But it does not say, changing this will change that. A causal constraint, cause, is a different type of rule. It must satisfy a stricter condition. It says, if you perform a minimal, controlled intervention to set the value of A to some specific state, independently of all other factors, then the value of B will change in a predictable way according to a specific functional relationship that is invariant under that class of interventions. The key is the intervention. An intervention is not just another observation. It is an active manipulation that breaks the normal passive flow of phi in a controlled way. In the triunity, an intervention is a targeted modulation of phi along one of the three echo dimensions. Omega intervention, you modulate the timing, rhythm, or rate of a process. For example, you inject a pulse of energy at a precise moment, changing the local omega derivative of phi. Or you impose a periodic forcing on a system. K intervention, you modulate the spatial pattern or boundary. For example, you insert a barrier, change the shape of a container, or laser ablate a specific cell in a tissue, changing the local K structure of phi. 3. V intervention, motion. You modulate the propagation or frame. For example, you apply a force to change momentum, you rotate the reference frame, or you inject a substance that changes the coupling between elements, changing the local V coupling of phi. A causal claim, therefore, is not complete without specifying which interventions are allowed and what invariants should remain. The rule C cause must predict not just what B is when A is observed, but what B will be when A is set by intervention. Formally, we can denote an intervention on A as do A equals A, where do represents the act of forcing A to take value A, cutting it off from its usual causal parents in the phi network. A causal rule has the form C cause, B equals f of do A, where the function f is invariant under the class of interventions do A. This means if you do A equals 1, you get B equals f of 1. If you do A equals 2, you get B equals f of 2. The function f is the same. This is intervention robustness. In contrast, a correlational rule, C-core, makes no claim about the do operation. It only describes the joint probability. P that B of BA, this is the probability of seeing B given that you see A. This is observation conditioning. The critical insight is P that B that do of A is not, in general, equal to P that B that A. They are mathematically different objects. Mistaking one for the other is the source of the confusion. This connects decisively to energy as tally. Energy tallies can correlate beautifully between A and B, while being entirely non-causal. Two gauges on a dashboard, say engine temperature and cabin temperature, might show a perfect correlation, and their energy flows might seem linked. But intervening on the engine temperature gauge by physically bending the needle does not change the cabin temperature. The correlation was driven by a hidden common cause, the actual engine heat. Causality is not a number. It is what remains invariant under interventions. The energy accounting only becomes causally meaningful if it holds under interventions on the putative cause. Consider a classic example: ice cream sales and drowning deaths. These are strongly correlated. Higher sales, more drownings. The correlational rule CCC is true, but the causal rule, ice cream sales cause drowning deaths, is false. Why? Perform the intervention test. Imagine you could, as a policymaker, forcibly increase ice cream sales on a random Tuesday in winter. A V intervention on the economic flow. According to the false causal rule, drowning deaths should spike. They would not. The correlation is driven by a confounding variable, hot weather, a hidden omega and K condition. Hot weather, increased temperature, a phi pattern, causes both increased desire for ice cream and increased swimming, leading to more drownings. The intervention on ice cream sales does not break the link from weather to drownings, so the prediction fails. The firewall role, therefore, is that of the intervention enforcer. When a rule G is presented with a causal claim, A causes B, you demand the intervention test. You ask, has a controlled intervention on A been performed? Or can its effects be reliably predicted from a causal model that has survived such tests elsewhere? What is the class of allowed interventions? Does the relationship hold under those interventions? Let us state with crystalline clarity what is allowed and what is forbidden at this gate. What is allowed? You are allowed to discover and report correlational constraints. This is valuable descriptive science. You are also allowed to propose causal hypotheses. However, to license a rule as causal, you must provide evidence of intervention robustness. This evidence can be 1. Direct experimental intervention, randomized controlled trial, a physics lab experiment. 2. Natural experiment, a quasi-intervention provided by nature, like a sudden policy change or a geological event. 3. Deduction from a broader causal theory, e.g. from Maxwell's equations, that has itself survived myriad intervention tests. The rule's scope object S must explicitly include the intervention class for which it is valid. What is forbidden? You may not claim a causal relationship based solely on observational correlation, no matter how strong or statistically significant. Use causal language, drives, controls, leads to, for a rule that has only passed correlational tests. Assume that because a model fits observational data well, its parameters represent causal strengths. Dismiss the need for intervention testing by appealing to practicality or ethics without downgrading the claim to correlational. What happens when the check fails? The license consequence is precise and restrictive. Fail, downgrade from causal rule to correlational descriptor. The rule's license is amended. Its type is changed from causal constraint to correlational constraint. Its usage is restricted. It may not be used to predict the outcomes of interventions. It can only be used for passive prediction or description within the observed regime. It becomes a weather vane, not a steering wheel. Now we must state the explicit prediction and falsification for the causal versus correlational distinction. Prediction, if the rule is causal. After a minimal controlled intervention on the putative cause A, the correct causal constraint yields predictable, reproducible, omega point k-Buck volt changes in the effect B, consistent with the rule's scope. If you do A, you get a specific rule-predicted change in B's time signature, omega, spatial pattern, k, or motion, v. The prediction is successful manipulation. Falsification condition for a causal claim. If the relationship collapses under intervention while the mere correlation remains strong in passive observation, it was never causal. For example, if you force change A and B does not respond as predicted, but in untouched systems A and B still move together, then your rule G was a correlational descriptor, not a causal constraint. The falsification is interventional failure. A profound example from medicine is the history of hormone replacement therapy, HRT, and heart disease. Extensive observational studies, correlational data, showed that women taking HRT had lower rates of heart disease. The correlational rule, CIRR, was strong. Many infer the causal rule. HRT causes reduced heart disease. This led to widespread prescription for prevention. Then, large-scale randomized controlled trials, the gold standard intervention test, were conducted. Women were randomly assigned to take HRT or a placebo, a direct intervention via biochemistry. The result? The intervention group showed no benefit and even potential harm for heart disease. The causal claim was falsified. The original correlation was likely due to a confounding variable. Women who chose to take HRT were also more likely to be from higher socioeconomic groups with better overall health and healthcare access, a hidden KV condition. The firewall would have downgraded the initial causal claim to a correlational descriptor, preventing a massive public health misstep. Let us explore an analogy from the intricate socioeconomic dynamics of opium poppy cultivation in Helmand province and its relationship with regional grain prices. An agricultural economist studies the region for a decade. He observes a tight inverse correlation. When the yield of opium poppies in Helmand is high, the market price of wheat in Lashkargah falls. When poppy yield is low, wheat prices rise. The data is robust across seasons. He posits a causal rule G. High opium poppy production causes low wheat prices. The mechanism seems plausible. Poppies are more lucrative, so farmers switch land and labor from wheat to poppies, reducing wheat supply and thus, that would cause wheat prices to rise. The observed correlation is the opposite, so he revises. Perhaps opium money floods the local economy, increasing demand for food, which should raise wheat prices. But the correlation shows the opposite. Puzzled, he settles on a complex story about market distortions and speculative holding. He publishes his causal rule. A policy advisor, trained in causal firewall checks, is skeptical. She demands an intervention test. She designs a thought experiment. Suppose, through a secure international development program, you could directly intervene to artificially increase opium poppy production in a controlled, isolated district while holding all other factors, weather, security, international opium prices, constant. A K intervention on land use and a V intervention on agricultural input. According to Rule G, wheat prices in that district should reliably fall. But the advisor knows the local context deeply. She identifies the likely confounding variable, security conditions. The hidden fee pattern is the presence or absence of Taliban control and associated conflict. Here is the true causal map. 1. High Taliban control. A phi pattern of security coercion creates conditions permissive for poppy cultivation. They tax it, protect it, and simultaneously disrupts wheat supply chains. Roads are dangerous, mills are closed, traders flee. This leads to both high poppy yield and low wheat supply, causing high wheat prices. This would create a positive correlation. 2. Low Taliban control, government control, discourages poppies through eradication campaigns and simultaneously allows wheat markets to function, leading to both low poppy yield and high wheat supply, causing low wheat prices. This also creates a positive correlation, but the data shows an inverse correlation. The advisor realizes there is a second, stronger confounding variable: international opium price shocks. A sudden drop in the global price of opium, an external V intervention on the market, makes poppy cultivation less profitable. Farmers preemptively switch some land back to wheat in anticipation, increasing wheat supply and lowering its price. Thus, low poppy yield, due to low price, correlates with low wheat price, due to increased supply. Conversely, a high global price causes a rush to poppies, pulling land from wheat, reducing wheat supply and raising its price. Thus, high poppy yield correlates with high wheat price. This is the observed inverse correlation. Both correlations, from security and from price shocks, are real, but they are driven by hidden common causes. The proposed rule, poppies cause wheat price, fails the intervention test. If you directly intervene to increase poppies by subsidizing farmers independently of global price or security, the effect on wheat price would be ambiguous and certainly not reliably inverse. It would depend on whether the intervention displaced wheatland, which is a separate mechanism. The correlation is not causal. The firewall's license consequence is applied. The economist's rule G is downgraded to a correlational descriptor. Its license now reads: inverse correlational constraint between Helmand poppy yield and Lashkar Gah wheat price under early 21st century conditions of fluctuating security and global commodity markets. It is forbidden from being used to predict the outcome of an eradication program or an agricultural subsidy intervention. To make those predictions, you need the true causal model involving the hidden variables, security dynamics, and global price signals. In Holophase science, the poppy yield and wheat price are two derived patterns, A phi and B phi. The security condition and global price are other facets of phi. The economist saw a correlation in the tapestry and guessed at a thread of direct causation. The firewall enforcer demanded the intervention test, revealed the hidden common drivers, and prevented a policy based on a false lever. This happens constantly in science. We see a correlation between gene expression and disease, between CO2 and temperature, between monetary supply and inflation, and we must, before acting, perform the rigorous causal check. This discipline is the rigorous embodiment of the episode 11 axioms. Rules do not become real by elegance, consensus, or tradition. They earn a license only by surviving falsification, variation, independence, and scope discipline. The causal check is the ultimate test of variation and independence. It creates variation through intervention. It tests if the rule is independent of the confounding paths by cutting them. A rule that only holds when everything else is passively observed has not earned a causal license. And the cardinal rule: when a rule fails, we do not believe harder. We tighten, downgrade, or retire its license. When a causal claim fails the intervention test, we do not add epicycles to the theory. We downgrade it to a correlational observation. We tighten its scope to passive observation only. We retire its use for control. The skill you gain from this part is interventional thinking. You learn to translate every A causes B claim into a mental experiment. If I could reach into the world and wiggle A while holding everything else as constant as possible, what would happen to B? If you cannot answer that, or if the answer contradicts the claim, you have not found the cause. You have found a correlation. This skill is the foundation of effective science, engineering, and policy. This skill has immediate, vital application. In machine learning and AI, predictive models excel at finding correlations. But using them for causal decisions, like granting parole or prescribing medicine, requires estimating PB, which is a different, much harder problem. The firewall warns against correlation-based causation in AI systems. The correlation between atmospheric CO2 and global temperature is robust. But to claim CO2 causes warming requires intervention-style evidence. Physics-based models that survive tests like predicting the spectral signature of warming or the response to volcanic eruptions, natural interventions, not just curve fitting. Does education cause higher income? Observational data shows a correlation, but intervention tests, like randomized trials of scholarship programs, are needed to separate the effect of education itself from the confounding factors of family background, innate ability, and social networks. A gene is correlated with a disease. Is it causal? The intervention test is the knockout experiment. Disable the gene in an animal model, a K intervention on the genome, and see if disease risk changes. Without this, it's just correlation. Finally, let us summarize the epistemic function of this part. Let us crystallize what we have built. We have defined the causal versus correlational constraint distinction. This firewall mechanism mandates that a claim of causality requires evidence of intervention robustness. The rule must hold when the putative cause is actively manipulated. Correlation is passive co-occurrence. Causality is active invariant response. The firewall acts as an intervention enforcer. It blocks the licensing of causal rules that rely solely on observational correlation, demanding evidence from controlled experiments or solid deductive chains from already verified causal theories. The explicit prediction for a causal rule is successful manipulation. Predictable, reproducible changes in the effect under interventions on the cause. The explicit falsification condition for a causal claim is interventional failure, the breakdown of the relationship when the cause is actively set, proving it was merely correlational. The license consequence is downgrade and restriction. The rule is reclassified as a correlational descriptor, and its use for intervention-based prediction is forbidden. This strengthens the firewall by adding a manipulability check. It ensures that the rules we use to change the world are actually about how the world responds to change. It separates the map of associations from the lever of control. With this, the firewall can now detect rules that are descriptively accurate but operatively false, rules that seem to explain the past but cannot guide future action. This is a critical defense against magical thinking, where we believe that because two things have always been together, we can use one to control the other. The causal check grounds power in understanding. It says, you only truly understand something when you can predict not just what it does, but what it will do when you poke it. If you want to see the full mathematical derivations and exact equations behind this idea, you can search for Holophase on Zenodo. There you will find the scientific papers that this audio journey is built on. Carry the light of the intervention designer. Be ruthless with causal claims. Demand the poke. In a world drowning in correlations, the ability to distinguish true causes is the most valuable skill of all. It is the difference between being a passenger of phi and being a navigator. Now, we must confront a final, even more subtle deception. Even a relationship that passes an intervention test can be a lie. Even interventions can lie when a hidden driver is steering both sides. This leads us to the last, most insidious trap, the hidden confounder that survives our pokes. Salam and peace be upon you.